So we got this planar lamina, a thin flat sheet of some material. The density at any spot is measured in mass per unit area, mass over area. And then we just, for note number 3, said that if the region R corresponding to a lamina is of uniform density, Greek symbol rho, then the mass is actually going to be just equal to rho times the area of the region. Because if you multiply density, mass over area, times area, you're left with mass. Now, here's the thing, you guys. The area of the region, if you think about it, so think of this guy as your planar lamina, the area of that region is expressed by the double integral that we talked about a little bit ago today and also the other night. So remember what that is. It's the integral from, okay, A to B. Think of a representative rectangle here. And the bottom of that, the function that gives you the bottom of that is your lower limit of integration. The function that gives you the top of that representative rectangle is your upper limit of integration. And then dy dx. So, multiply that. That's the area. So you multiply that times the rho that we have right here. And that's another way to express the mass of the planar lamina. Now, in Calculus 3, rho will not be a constant. And you actually have to have it on the inside of the integral. Because it is a constant, we can move it in there easily enough. And I'm going to do that for reasons that will soon become apparent, I think. So we get that the mass is equal to the integral from a to b of the integral from g of x to f of x. Bring the constant to the inside, rho, dy dx. And that's your one way to express the mass of the planar lamina. Now, there's a reason for doing that. I'll make it clear very soon. Okay. Now, number 4, note number 4, try to keep that in sight for a second. Note number 4, okay, by analogy with the center of mass for a finite number of point masses, we're going to create a formula for the centroid of a planar lamina. So think about what that formula was. For if you have n point masses, then the formula we came up with earlier was x bar y bar. To get x bar, you take 1 over m times the sum from I equals 1 to n of m sub I times x sub I. So I mean, that's not as complicated as it looks. You have the sum of all the masses is m. And then what does this formula represent for x bar? It represents, m1, x1 plus m2, x2 plus ... all the way until you get to mn xn. That's what this formula represents. Similarly, for y bar, this is y bar. And so if you want the place where the planar lamina is going to balance, imagine that this guy is my planar lamina now. So, and it's actually a better illustration than what we looked at earlier. So this guy's my planar lamina. Get some light on the subject, maybe. Okay. And where is it going to balance? Well, because it's actually a clipboard, it's going to be a little heavier on the side with the clip, isn't it? So you wouldn't expect it to balance. You wouldn't expect it to balance right in the middle of the rectangle, like if this clip weren't here. So this is changing the mass a little bit, isn't it? So where is it going to balance? Well, I'm going to have to cheat. To get it to balance, I'm going to have to cheat, just like with the fulcrum, and put the pencil a little bit closer to the side with the clip. And it starts to almost balance. And you can tell I'm not quite in the center. I'm not centered the other way either. So getting close. There, that's pretty close. That's as close as I'm going to get. But I'm a little bit this way with the pencil because of the that mass down there. So what we're trying to do is figure out where to put the tip of the pencil. That's X bar, Y bar. Okay. Now, this guy is a continuous mass, right? So we don't have discrete little point masses that such that we can add together their masses, the m sub I times the x sub I. We can't do that here. So by analogy, we need to do the same thing with an integral. So go ahead.
I don't think we see what you're doing with your.
You had to look at my picture, right? I mean, right?
We don't see the picture.
You don't see my picture when I'm talking?
Like, are you looking at his actual video? Like of him?
When if you have your settings, well, there's more than one way to set up how to see who's speaking, but if you have it set up so it automatically puts in your little window who's speaking, you should be able to see the person who's speaking. So if you see my name in a little rectangle, you can see it's lit up with a little yellow line underneath. That means I'm talking. And if you have your settings right, you should be able to see my video. Am I correct, you guys? Yeah.
Yeah, that's how it is for me.
Yeah.
You have a video?
Yeah.
Okay. It's okay. I'll just keep.
Okay. So I'm sorry you couldn't see that. Do you see when I turn off the share, do you see me then? Nancy?
I just see the white screen.
But when I turn it off, can you see me? When I turn it off sharing the screen?
Nothing's turned off. I just see the white screen.
No, I'm not. So I'm saying I'm going to stop the share for a second. I'm just curious, see how this works. So if I stop the share, so now you don't see my OneNote screen. Do you see everybody's picture?
I just see one person's picture. I see other people's pictures, but I don't see.
Okay, play with your settings. You should see up in the right-hand corner speaker view, and you can play with that to see if you can see who's speaking.
Yeah,
so you should see a grid of rectangles, much like the grid of rectangles I drew earlier, right? And then it all relates back to calculus. And then if you hit speaker view, you should be able to play with the view as far as who you see.
Okay, I don't know.
Okay.
All right.
Okay, we'll have to pick that up another time. But if you want to stay after class or something, we can play with the settings and see what you see. So okay, so back to what I was talking about. Okay. So we're going to create an integral that looks somewhat like this for x bar. And we're going to create an integral that looks somewhat like this for y bar. That's the upshot of this discussion. Okay. So number 4, by analogy with what we were just talking about, the centroid of a planar lamina is dun 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 dun. Okay, we're still going to call it x bar, y bar. So what the heck is x bar? Okay. So think about that formula above. We had 1 over m, we're going to keep that. And instead of the sum symbol, we're going to have the double integral, a to b, g of x to f of x for our limits of integration. And then remember we had m sub I times x sub I. Well, I'm going to write it as, let's write it as, okay, remember the row here, we need that in there. And then I'm going to put instead of m sub I, x sub I, it's kind of like x sub I, m sub I. So okay, I know you don't see it yet, but that is, in analogy, that's what we had. So for the finite number of point masses, we had 1 over m times the sum, I equals 1 to n, m sub I, x sub I, remember that? That's what this guy is kind of emulating. So how do you see that? Well, look, remember how you think of dy dx as the area of one of those tiny little boxes in that grid that I created earlier? Well, if you multiply the area of one of those tiny boxes by rho, then you have what I would call a little mass element. So that rho dy dx is kind of like the m sub I here. The x is kind of like the x sub I, and the double integral symbolism is like the sum. And so this integral will do the same thing for an infinite number of points in your planar lamina that this formula down here did when we had a finite number of points. And then, and it simplifies, so don't worry, we're going to get a simpler formula in just a second. And then the y bar. Well, it's going to look very similar. It's going to be 1 over m integral a to b of the integral g of x to f of x. But instead of having x in there, just like the formula above, we're going to have a y in there. Remember, we had y sub I. So like that, we're going to have a y in there for y bar instead of an x. So we have y and then rho dy dx. Okay. So that first guy is x bar. After the comma, that's y bar. And it's written in the form of an ordered pair to emphasize the fact that if you calculate those coordinates, that will be the center of mass for any particular planar lamina. Now it does, whoops, I ripped my earpiece off. Okay, it does simplify. And I don't want this symbolism to scare you because we're just going to end up using a formula and doing some integrating when all is said and done. But it does simplify a little bit. Look, in Calculus 3, these are your formulas, by the way. So this would be the Calc 3 version. But it does simplify because we have the assumption that rho here is a constant, that your planar lamina's density is uniformly distributed. So rho is a constant, which means you can leave it out front like we had earlier. And if you have the rho over, if you bring this out front, you have rho over m. But you know that m is density times area. So those guys cancel. And you just have 1 over area out front without the rho in there in the Calculus 2 version of the formula. And so it does simplify because of that. So we get that the actual formulas we're going to use, 1 over a, double integral a to b, g of x to f of x for the limits on the integral, and then just x dy dx. That is the formula for x bar. And then 1 over a, integral a to b, integral g of x to f of x of just y dy dx. That formula after the comma, that's y bar. So I'm not going to ask you to derive what I just derived for you. But this is a formula that you guys can use. Now realize there's 3 integrals going on here. There's an integral that gives you area. You're going to find that first. And then multiply it times this integral to get x bar, and 1 over a, that is, times that integral to get x bar, and then 1 over a times this integral to get y bar. So you have to calculate in these examples 3 integrals. And again, the beauty of doing it this way, it's a little steeper learning curve, but then you get formulas that are going to come in handy once again in Calculus 3. If you look at the formulas in your book, they're equivalent to what we have here, but they don't look a whole lot like them, and they're confusing. They don't have that relationship that they look like the formulas for a finite number of point masses. So this really is a better way to go, especially if you're going into Calculus 3. Okay, so keep these
Professor?
formula. Yeah.
I just have a quick question on the clarification for when you're saying rho, that's just density, right?
Rho is density, yeah.
Okay. All right. Thank you.
Okay. So let me show you how to actually use these formulas. It's not as bad as it looks. So in this example, we have find the centroid of the lamina with the given boundary equations. We have y equals 1 over x, y equals 0, x equals 1, and x equals 2. So let me, I think I can draw this in just the first quadrant. So let's draw a picture of our planar lamina. Okay, y equals 1 over x. If you plot like just a couple of values like 1, x equals 1, and x equals 2, maybe x equals a half as well. You'll see very quickly if you plug in 1 for x here, of course, you get 1 for y. You plug in 2, you get a half. If you plug in a half, you flip and multiply, and you get 2, and you get this guy. It's actually part of a hyperbola. And we're only graphing the part in the first quadrant. There's another part in the third quadrant that we're not interested in. And then y equals 0 is the x-axis, so that's a boundary down here. And then x equals 1 is here. X equals 2 is here. So this is our planar lamina. And you could actually erase the other parts of it if you wanted to. Okay, so if you want to find the center of mass. So does everybody understand what it is we're trying to do then? If you just consider this region that I drew, we want to find the point at which if we put this region horizontal, it would balance. Like for those of you that can see it, like where would this balance? If we put it at the tip of a pen or a pencil, where would it balance? Where would that balance point be? Somewhere over here. So you could take, it's fun to take a guess at it. I don't know. I'm guessing over here somewhere. And if I draw my point big enough, I'll be right. But let's find it for sure. So we want to find that balance point, that centroid, center of mass. It's all the same thing. Balance point, centroid, center of mass, all the same thing. So how do we do it? How do we go about it? Well, we have to find the area of the region first, always. And so even though I don't need to, I'm going to set it up as a double integral. Very quickly, we'll go to a single integral. But if you set it up as a double integral, it's going to help you later on. So draw your representative rectangle. I don't know if that's dark enough. Let me try green. Draw your representative rectangle. That's a good habit to get into for Calculus 3. And then set up the double integral symbolism. And then the dy dx. The integrand is always 1 when you're finding the area here. And the outer limits of integration coincide with just what x runs from. So the differential dx is on the outside. That reminds you that you're setting up the outer integral with respect to x. So x is constant and it runs from 1. The outer limits of integration are always constant. The lower and upper boundaries, that is. And x runs from 1 to 2. And then if you look at the rectangle itself, the bottom of that rectangle gives you the lower inner limit of integration. And the bottom of that rectangle is just y equals 0. It's the x-axis. And the top of that rectangle is given by the function that gives you 1 over x. So there's your upper inner limit of integration. So you would say this as the integral from 1 to 2 of the integral from 0 to 1 over x of dy dx. Okay, now very quickly, I don't even think you need to evaluate it to realize that that inner integral then is just going to be equivalent to taking 1 over x minus 0, which is just 1 over x. And so if you evaluate that inner integral, if you don't believe me, evaluate it. Evaluate that guy in the purple brackets there. And if you did that, you'd integrate, you'd get y here, integrate with respect to y, you get y evaluated from 0 to 1 over x which I'm ignoring the outer limits of integration just for scratch work, which if you apply the fundamental theorem, you just get 1 over x plugged in for y, plug in 0, and you get your integrand for your outer integral if you do that. But you already knew that from your experience in chapter 6. Again, the real power of the double integral is going to come in handy later on, not right now. Later on in the problem, that is. Okay, so we need to integrate that to find the area of our planar lamina. Okay, so let's do that. Help me out, you guys. What's the integral of natural? Oh gosh, I said it. I was going to say it. What's the integral of 1 over x?
ln.
How'd you know? Ln of x. And we don't need to worry about absolute value here because we're integrating from 1 to 2. Those are positive values. So we're evaluating that from 1 to 2. And that's natural log of 2 minus 0 because the natural log of 1 is 0. So the area is the natural log of 2. Okay. I'm going to back off the view. Now we're going to find x bar and y bar. And I'm going to show you why it's so important to remember the double integral, especially in Calculus 3. So I taught Calculus 3 for years, and I want to teach it again, but I've been too busy. And I've come up with a good way to teach this section because it's really hard to remember all the formulas. So the reason you set up the area as a double integral is you can use that as a mnemonic device for x bar. So look, x bar, if you think of that formula, just the generic formula above, remember what it was? It was 1 over a times that double integral a to b, g of x to f of x. And then we stuck in an x, and then it was dy dx, right? That's the formula we were talking about for the first coordinate, this guy up here. Look at that formula. Look at that formula, the right side, and then look at the double integral for area. All you have to remember is to stick in a couple of more items, and you've got it. So if you can come up with the double integral for area, then all you got to remember to do is multiply by, well, to get x bar, to multiply by 1 over that area, in this case, natural log of 2. And then the limits of integration, you don't have to think about it. They're exactly the same. 1 to 2, integral 0 to 1 over x. And then in here, remember what you do, you stick in an x and then dy dx. So by setting up this area integral, which you'll have to do in Calculus 3, you won't have a choice because it won't be this simple. Because that rho, that density, will actually be a function with 2 inputs in Calculus 3, and you'll have to be evaluating that to get the area. In other words, you'll have a rho in here, and when you get to Calculus 3, we don't have to worry about that here. Okay. Now, let's evaluate that guy. And that'll give us x bar. Okay, so if we evaluate this guy, we evaluate the inner integral first, but it's with respect to y. So x is a constant with respect to y. So if I evaluate that inner integral, I'm just going to get, well, x times y. X is a constant with respect to y. And then I can leave x on the outside of the evaluation brackets, and don't forget the dy is gone, but the dx is still there. So what I did was I integrated x with respect to y, but that's just going to be x times y. And then I have to evaluate it from 0 to 1 over x. And so these are my evaluation brackets. Now, fundamental theorem says, oh, I've got to plug in 1 over x for y. And then I've got to subtract off what I get when I plug in the bottom limit, 0 for y, but that's just 1 over x. So I get x on the outside still, times 1 over x dx. And that's just x times 1 over x, that's just 1. So I get the integral from 1 to 2 of 1, or just dx. We don't even have to put the 1 in there. And if you evaluate that, oh, and then what did I not put out front? 1 divided by the natural log of 2. Don't forget that. 1 over area, right? That's what the area was. natural log of 2. And then you evaluate that, and you just get 1, because when you evaluate this integral, you get 1 with respect to x. You integrate 1 with respect to x, you get x. You evaluate it from 1 to 2. And that's just going to be 2 minus 1. So that's just 1 times 1 over natural log of 2. So 1 over natural log of 2 then is x. Follow the equal signs. That's x bar. And then we need y bar. Well, wait a minute. Let's go back up here and use either the area integral or the x bar integral as a model to help us set up y bar. So y bar is going to look just like this, except instead of sticking in an x, we stick in a y. So it's going to be 1 over area. That's 1 over natural log of 2. Integral, actually, if we focus on this one, then it'll have the particulars of this problem. Integral from 1 to 2 of the integral from 0 to 1 over x. And then instead of an x, we need a y, dy dx. So we evaluate that integral. Let's go ahead and do that, because it'll be a little bit different. So we have the 1 over natural log of 2 on the outside. Integral 1 to 2 doesn't go anywhere. If you evaluate this guy, this inner integral that is, and you integrate this guy, oh, yeah, it is with respect to y. So what do you get when you integrate y with respect to y? What do you get? I just want to make sure you're paying attention still. What do you get? So just integrate this. Y with respect to y. What do you get?
Y squared,
Y squared over 2. So 1/2 y squared, same thing. Evaluated from, now I'm going to leave the constant on the outside of the evaluation brackets, 0 to 1 over x. Those are the inner limits of integration, right? And then you have the dx on the outside. Okay. So applying the fundamental theorem on that inner quantity. By the way, if you want, you could pull this 1/2 out here and make it 1 over 2 natural log of 2. Let's do that. And then you just have to worry about 1 over x squared. So when you plug in a 1 over x to y squared, you get 1 over x squared minus 0. So I'm not going to write that down. That's what it becomes as a single integral. And then let's see, what do we get? 1 divided by 2 natural log of 2. Okay, this is x to the negative 2. So what do you get when you integrate that? Add 1, divide by the new exponent. Wouldn't you get negative x to the negative 1 or negative 1 over x? I'm going to pull that negative to the outside and write the 1 over x on the inside of the evaluation brackets, evaluated from 1 to 2. So that negative would be in there, but I don't need to have it in there. And then when I do the evaluation, I'll have plug in the upper limit, 1 over 2 minus 1, which is actually minus 1/2 on the inside. So the negatives will cancel, and you'll have a 1 over 2 natural log of 2 times 1/2, which is 1 over 4 natural log of 2. And if you follow the equal signs, that was y bar. So then the balance point, the centroid, whatever you want to call it, x bar, y bar, is going to be these two coordinates put together. 1 divided by natural log of 2, comma 1 divided by 4 natural log of 2. And then let me break out my calculator. And I'm not, let's see, I don't see it. My calculator's, my virtual calculator's having trouble, so I'll use my regular calculator here. So I just want to get a decimal approximation. 1 divided by the natural log of 2, ln of 2. That's about 1.4 if we round. And then let's see, 1 divided by 4 natural log of 2. That's about 0.36, close to 0.4 if you round. So 1.4, 0.4, what we're saying then, okay, 1.4, I don't know, somewhere, almost where I was pointing, for whatever reason I was pointing, what kind of where I put my rectangle, almost right there. And then up 0.4, well, let's see, that was 1, so 0.4, I don't know, down here somewhere. So it is cheating up towards this extra area up here a little bit. So your balance point, I don't know, if I draw it big enough, I'll hit it. It's in there somewhere. That's where it'll balance. I know I threw a lot at you. Thankfully, though, that's pretty much it for the new material. At least the new material that you haven't seen before. Any questions on all that? So let's go over it a little bit just to summarize. You're going to want to find the area. If you're asked to find the centroid, you're going to want to find the area of your planar lamina. And double integral wise, it's always, the first integral always goes from, you know, the x limits of integration, at least that's true in this class. In Calculus 3, you'll look at it from a different perspective. In certain cases, it'll be dx, dy, and then it'll be, the outer limits will be y goes from whatever to whatever. Here it's x goes from whatever to whatever. I'm not going to change that on you. And then y goes from the bottom of the representative rectangle. We're always going to have vertical representative rectangles here, g of x to f of x. Not that you have to do it that way. I'm just trying to keep it simple. And then dy dx. So that's your area. And then you use that area to find x bar. Remember that's, oh, just stick it in front of this integral. Just stick a 1 over a, which is what you get from that integral, by the way. And then, okay, the limits of integration stay exactly the same. And then you stick an x in for your integrand, x dy dx. And then the y bar looks exactly the same as what I just wrote down, except you stick a y in there. So integral 1 over a, integral a to b of the integral g of x to f of x. Now stick a y in there, dy dx. And that's the y. And I'm hoping, maybe, I'm not saying I'm hoping you like this stuff. I certainly didn't like it when I was in your shoes. But now the way I've put it together, I'm hoping you appreciate these formulas. Because the thing is, if you can remember a, you can remember x bar. And you can remember the formula for y bar then. And it took me years of teaching Calculus 3 to organize the information this way so that it's easier to remember, because it looks like in this class and in Calculus 3 that the formulas are just thrown in there and there's no pattern at all. So I'm trying to show you this pattern, and when you get to Calculus 3, you can remember this pattern. You can look up my Calculus 3 notes if you want on my website, and these formulas will be there. Any questions? Okay, probably a good time for a break. So let's take 10 minutes off, and we'll talk some more. So I need to give you the kind of the bare bones of section 10.5, simply because you need to know it for Calculus 3. So we're going to talk not about parabolas. You guys know all about parabolas. But let's talk a little bit about ellipses and hyperbolas, and you guys should know about those as well. But you know, if it's been a while, sometimes you forget. So conic sections, a cone in space is actually looks like two ice cream cones stuck together, and it doesn't stop like this. This cone actually, you know, it keeps going up forever and ever and out and back, but for picture purposes, you have to stop it somewhere. This goes down forever and ever. If you cut it in the right way, you could get a parabola. So you cut it with a plane, a flat surface. You could get a parabola indicated in yellow right here. Or perhaps a circle or an oval shaped object, if you cut it with the plane the right way, or maybe a hyperbola, which has two branches, one that goes, in this case, up and one that goes down. So by conic sections, what we mean would be the cross sections you get when you cut a cone with a plane. And you guys have seen parabolas before. I'm not going to talk about that. You've seen ellipses before, but it's not quite as common. So let me just remind you what the standard equations are. We already talked about them a little bit in here. So an ellipse is an oval-shaped curve. And there's two standard equations, x minus h squared over a squared plus y minus k squared over b squared equals 1. And if that's your equation, then, oh, you know what, I can cheat a little bit and use my drawing tool here. So let's say that's your ellipse. So the ellipse is the curve itself, the points that make up the curve. And the center of this thing, if this is its equation, the center is HK. And it has two axes that we're concerned with, a horizontal axis, if I could draw straight, that guy, and a vertical axis. In this case, the horizontal axis is the long axis, so we call it the major axis. And the axis perpendicular to that is the shorter of the two. It's called the minor axis. The distance from the center on out to what we call a vertex. You've got a vertex here, a vertex here. Vertices occur at the end points of the major axis. And that distance from the center on out to a vertex is called A. And that the distance from the center on the minor, that's on the major axis, it's called A. The distance from the center on out to the curve that is the ellipse on the minor axis is that distance is B. And so this is your standard form. We always think of A as being bigger than B. This is your standard form if the major axis is horizontal. And then the other one we consider is if you rotate this one 90 degrees, one way or another, then the long axis becomes vertical. And you get the equation x minus h quantities squared over b squared, a squared and b squared switch places, plus y minus k quantities squared over a squared. That's equal to 1. So it looks the same. And it would just be, the picture would just be this guy rotated 90 degrees. So rotate 90 degrees to get the picture.
Professor?
Yep.
Will this be on the final or is this just for Calc 3? Like just like a...
I would not shy away from putting this on the final. It's something that I'm hoping most of you already kind of know, right? But all you need to know is how to graph the thing and put it in standard form if you need to. So you need to know how to complete the square. So for instance, let's do this example. And so I'm not asking much. I'm not asking you to find any focus points or anything you might have heard of in the past. Just be able to graph, be able to graph an ellipse. And to do that, you need to be able to put it in standard form. So yet another example of completing the square to get this guy in standard form. So we have 9x squared plus 4y squared minus 36x plus 24y plus 36 equals 0. And we need to make it look like one of the above equations. So the way you do that is you group the powers of x together, 9x squared plus, or actually minus 36x. And then plus 4y squared plus 24y. And I'm going to move the 36 to the other side, make it negative 36. And then, do you guys remember what to do? Before I complete the square on the x, the powers of x, what do I have to do? Anybody remember?
Group x's and y's together.
Yeah, I did that. What do I need in front of the x squared to complete the square? Nobody remembers? I think you're just being shy. You need a 1 in front of the x squared. Remember that? So you could divide through by 9 to get a 1 in front of the x squared, but no, it's easier, better just to factor it out for the time being. So if you factor out a 9 from 9x squared minus 36x, you'd have x squared minus 4x left. Leave space to complete the square. And we're actually going to do the same thing to the y's in a minute. So we'll leave space for that. So to complete the square, then remember you take half the coefficient of the minus 4, get minus 2, and then you square that and add it. And that completes the square. Makes it so you can factor it as a perfect square. Now, you can't just add 4 inside these parentheses. You have to add something to the other side. What do you have to add to the other side?
Four.
Oh, take another look. What did you
Minus
really?
4, yeah.
What did you really add?
36.
There you go. So plus 36. You really added 36 because the 4 was inside the parentheses, and it's really multiplied times 9, isn't it? And then this guy, then x squared minus 4x plus 4 factors to be x minus 2 quantity squared. And then the 9 is still there. Everybody buy that? We're only halfway done. You get to complete the square twice. More for your tuition dollar. Okay, so now go to the 4y squared plus 24y. Same idea. What am I going to have to factor out?
4.
4, yeah, the lead term on the y squared anyway. 4, and then what's left? Y squared plus
6.
6y, and then what do? Take it from there. What's half of 6?
3 and then square it, 9.
Okay, so you had 9 in here, but what did you really add?
36.
36 again. It's not always the same, though, is it? That's just a coincidence. And then y squared plus 6y plus 9 factors to be y plus 3 quantity squared. That's why you write it down, because it's going to be involved in the factorization. When you take half the coefficient of the y, write it down. And you still have a plus 4 on the outside. And this is just 36. What do we need, you guys, on the right side to get it in standard form? It doesn't have to be on the right side, but that's usually how we put it.
I think you go to 1, right?
You got to get a 1. So you go divide by 36, divide by 36, divide by 36. And then I want to show you a trick that's pointless here, but in other problems, it's not pointless. So like on this one, you're multiplying by 936, and that actually reduces. So the 9 would go away. But in other problems, it won't. So in other problems, what you'd have to do is go x minus 2 quantity squared divided by 36 ninths. Multiplication by 936 is the same as division by 36 ninths. Now, of course, 36 ninths is just 4, so there was no reason to do that. 9 over 36 reduces to 1 over 4. But in other cases, it won't reduce, so you need to know that trick. So I'm going to do the same thing here. Multiplication by 436 is the same as division by 36 fourths. And so if these guys didn't simplify, this would be the standard form. But because it simplifies, of course, you're going to go ahead and simplify it. You're going to write it as x minus 2 quantity squared over 4 plus y plus 3 quantity squared over 9 equals 1. So for sure, you're going to see problems like that where you have to complete the square in Calculus 3. And you'll probably see it in the very first chapter in a much larger context. It won't just be this sort of problem where you're graphing an ellipse. You'll be graphing an ellipsoid perhaps in space. So yeah, it's one skill in a larger skill set that you need. Now, I'm hoping that you remember how to graph this ellipse. Is it tough to graph the ellipse? What do you start with? What do you think C stands for here?
Center.
Yeah, what's the center of this thing?
2, -3.
There you go. So you're going to start at the center, over 2, down 1, 2, 3. Do you remember how far left and right you go?
The bottom numbers.
Is it the bottom number exactly?
Square root of them.
There you go.
Half
So
of
go
it.
left and right, the square root of the number underneath the quantity involving x. X controls the horizontal, so that's easy to remember. So from the center, go left 2, go right 2. And then up and down, square root of that number, 1, 2, 3, 1, 2, 3. And just draw the best oval shape you can. It's not going to be perfect. And there's your ellipse. Any questions? Definitely something you need to be able to do. And the other thing you need to be able to do is you need to be able to write the parametric equations of the ellipse. Do you remember how to do that? I'll do it in the context of this example. So if all you were asked to do was graph the thing, the standard equation would be part of your answer, and of course the graph. But if like in chapter 10, you parameterize this thing, then here's what you have to remember. You can rewrite this first guy, x minus 2 squared divided by 4, as x minus 2 over 2, the whole thing squared. That's the same thing because the exponent splits up over division. That's the same thing as x minus 2 quantity squared over 4. We're kind of bringing out the exponent, I guess. And then y plus 3 over 3, the whole thing squared, equals 1. That's equivalent to that. And then do you remember what you do from here? Or what you could do from here? What does this remind you of? Something squared plus something squared equals 1. Does it remind you of your favorite trig identity?
The Pythagorean identity.
The main Pythagorean identity. So you could do this to come up with your parametric equations. You could set this guy, well, you've got a couple of options, but you could set this guy equal to cosine. So you could set x minus 2 over 2 equal to cosine. We'll use a parameter of t. And then if you solve that, for x, you would multiply both sides by 2 and then add 2. I think you'd get x equals 2 plus 2 cosine of t. That would be one of your parametric equations. The other one, you would set this guy equal to sine of t. So y plus 3 over 3 equals sine of t. And you've seen this before. Multiply both sides by 3, subtract 3. So what would you get? Y equals -3 plus 3 sine of t. And then t only has to go from 0 to 2 pi to trace out the whole thing. Otherwise, you're tracing it out more than once if you go to the left of 0 or to the right of 2 pi. So these would be your parametric equations. And I just wanted to remind you of that because you studied that in chapter 10 a little bit. And that for sure you're going to need to know, not only in this class, but in Calc 3. It's going to come up a lot. Okay, any questions on all that? I don't think I'll do hyperbolas tonight. I'll save that for next time so you have a chance to ask another homework question or two. I will mention the standard equation of a circle because, hey, a circle is an ellipse, isn't it? So just remember the standard equation of a circle is x minus h quantity squared plus y minus k quantity squared equals r squared. H and k is the center, r is the radius. And if you just divided everything by r squared, you'd have the standard equation of an ellipse where a equals b, a squared equals b squared, so a equals b. Just wanted to remind you, so the statement every circle is an ellipse is true, but the statement every ellipse is a circle is not true. And we'll stop it there, and then we'll just do a little bit on Monday with hyperbolas. But again, it won't be new material. It'll just be stuff I need to remind you about for Calc 3. Okay, any questions on ellipses? All right, so let's talk. If you have a homework question, let's do a little bit of that. We can talk about movies. Do they make movies anymore? I guess they release them directly to video now, don't they?
I think there was a bunch planned and they just like delayed them all.
Yeah. Anybody see any good movies on Prime or Netflix any recently?
I've been watching classics like I don't know. Sometimes I like to go through and watch like all of a particular actor. Like I did Tombstone with like Val Kilmer.
Tombstone's a great movie. I watched it when it first came out. That's how old I am. But yeah, I always liked that one. And yeah, Val Kilmer did a great job in that one. Yeah, so I need movies to watch. So let me know if you have one.
Have you seen The Secret Window?
What's that?
The Secret Window?
No. It sounds familiar.
It's a Stephen King movie that Johnny Depp was in.
Really? How old is it?
I think it was a 2000s movie.
Oh, okay, so been a while. Okay, Secret Window.
But it's phenomenal. Like, it's pretty good.
Cool. All right. Okay. What about homework questions? Anything I can help you with?
And we do number 5 off of 8.3.
Well, let's hold 8.3. Let's hold that till next time, since we. So that's due next week. I think it'd be better to maybe talk about something that's due this week.
I had one on 8.2 that I was kind of confused about.
So 8.2 was 8.2 due this week, or was that last week? I think it was due this week. What was it?
It was number 28. That was the last one.
Well, we already did that one. No, we didn't. Yeah, we did. I sent you a copy of that one.
I'll go check that out.
Yeah, so check your email. I sent you a copy of the full solution of that one.
Professor?
Yep.
Could we do number 17 from that section, please? 17. So, yeah. Find the area. Yeah, I like this one. So not that I don't like the others, but it's just we haven't done it yet. Okay, so 17. We have x equals the square root of a squared minus y squared.
What section is this?
This is 8.2. And it's defined for y between 0 and a divided by 2. It says the given curve is rotated about the y-axis. Find the area of the resulting surface. Okay, so it's part of a circle, you guys. Let's draw this. I think it'll be helpful to draw it. So if you were, I'm going to draw the whole circle and then I'll erase part of it because it's not the whole circle, and we'll talk about that. So I'm going to use my little cheating device here so that I can get a better looking circle, hopefully. Now, if you think about it, the reason I know it's a circle is if you square both sides and then add y squared, the full circle would be x squared plus y squared equals a squared, wouldn't it? But because we're only allowing y to go from 0 to a over 2, it's not going to be the full circle. So we'll have to take part of it away the way I'm doing it, or you could just draw part of it. So let's imagine that that's actually a circle. Probably not quite a circle. It's probably an ellipse though. And then, so A would be, on the x-axis that is, would be here, and then on the y-axis, A would be here. But let's see, A is allowed to go from 0, y is allowed to go from 0 to a over 2, so a over 2 would be like right there. So we've got some erasing to do. Let me get my eraser out. So, so y is only allowed to go from 0 to a over 2. That means I need to erase the whole, what, bottom half? Plus some, right? So what? So erase the part above a over 2, right? So I think now that's, let me see here. Oh, yeah. And also, because it's x is positive, you erase this part. That's what I wanted to check on. So really, you just have this curve, this little piece of the curve, and that's what you're rotating about the y-axis. Does that make sense? So you're cutting it off there, essentially. Just the curve in red about the y-axis. And then, so you can imagine what that would look like. It would look like part of a sphere when you rotate it, wouldn't it? And you're finding the surface area of that part of the sphere. Does that make sense? Okay. So write down your formula. Now, generically speaking, the formula we're going to use here is the integral over the curve. That's the curve C. So over C, 2 pi r ds. And just remembering that symbolism can lead you to the more complicated formula, right? Because you know what ds is. ds, if you do it in terms of the parameterization, which you don't have to here, I noticed in your homework, a lot of you didn't like call xt or yt, but I'm going to do it that way because it helps in Chapter 10 when you're talking about surface area in Chapter 10. So in terms of a parameterization, remember ds would be dx dt square root, dx dt squared plus dy dt squared, square root of all that, and then dt. And so by writing those formulas down, it reminds us what we need to find. First of all, if I do it my way, I'm going to have I'm going to want to have a parameterization, and when I have x in terms of y, then automatically I'm going to do what? I'm going to call the input variable, which is y, t, or whatever letter you use for the parameter. And then automatically x is the square root of a squared minus t squared. And I get my parametric equations that way. Alternatively, you could use the appropriate equation that they give you in this section for when x is defined as a function of y. But it's equivalent. And if you do it my way, there's only one formula to memorize once you get your parameterization. Okay, so you guys, what does all this notation then, especially the ds part, tell us we need to find?
The derivatives of the function of x and y.
There you go. I'll do dy dt for you because I'm that nice of a guy. Let's see, dy dt, that's a tough one. 1. Okay, that wasn't that nice, I know. What's dx dt turn out to be? So think of it as a squared minus t squared to the 1/2 power. Well, what's that going to be? Derivative, bring down the 1/2. What do you get when the smoke settles? Are y'all still here? You're quiet tonight. Except when we talk about movies. I got a couple of reactions from that.
I think I have 1/2 quantity a squared minus t squared to the negative 1/2 power.
Yeah, but then what about the chain rule though?
Oh, then
Times
quantity
negative 2t.
So yeah, so I see where you got what you said. So you took the exponent down 1/2 a squared minus t squared, and then that'll be subtract 1 negative 1/2. But then yeah, you got to take the derivative of what's inside, which would be minus 2t, right?
Yeah.
But then okay, I'll do some erasing, I guess. So minus 2t. Oh, but then the 2's cancel, don't they? So just what? Minus, and that negative will go away when we square it. So minus t, and then I guess I could write it like this, over the square root of a squared minus t squared. You guys buy that?
Yeah.
All right. And then it actually works out when you have these formulas with these square roots in them like this, for the derivatives, it actually works out pretty nicely. So that, let me squeeze in ds right here. So ds then would be the square root, big square root, of this guy squared. Well, for this part of it anyway. Oh, and so the negative's gone, and then you have t squared up top, and then just divided by a squared minus t squared for the dx dt squared. Everybody see that? Then you add in the 1 squared. That's not so bad. Square root of all that. But then look, 1, if you think of 1, in terms of what the common denominator would be, you'd want to multiply 1 by a squared minus t squared, top and bottom, right? And get a single fraction underneath that radical. That's going to be helpful because things are going to cancel nicely if we do that. Square roots are going to go away if we do that. So now look, the denominators are the same. If we keep the denominator and add the numerator, what's going to be left up top in that numerator underneath the radical?
A squared.
Just the a squared, because the t squareds will cancel. And then you'll have what? A squared minus t squared in the denominator. Everybody buy that? Okay, and then what does that give us though? That gives us what? Just if we split up the radical, what? A over what? The square root of a squared minus t squared? Everybody buy that? Any questions on that? Okay, so then let me go ahead and try and fill in this formula then. And I think nice things will happen there as well. So that S then is going to be, I'm going to pull out the 2 pi. And then we're going to have the integral from, okay, if you look at the picture, we're integrating with respect to t, but that's t is y, right? So the limits of integration you're going to get for t, but t is y, so you're going to think about y. What does y go from? That's the same as what t goes from. So in the picture, what does y go from?
0 to a over 2.
Okay, so 0 to a over 2. Okay. And then what's r? We're rotating about which axis? The y axis. So if you draw an r, is okay, r is a horizontal value, so that's an x distance, isn't it? And what is x in terms of t but the square root of a squared minus t squared? So my r that I'm going to stick in the formula then is going to be the square root of a squared minus t squared. But I mean, that's not bad news because look, in the denominator of ds, and by the way, if we're really going to call this ds, I suppose we need a dt on the end, don't we? A little bit of symbolism mop up there.
look, the denominator of that guy has a square root, so good things are going to happen. So when we stick in the ds, we get a over the square root of a squared minus t squared, and then a dt right there. And then we get this nice cancellation. And it's not near as bad as it looked. In fact, a is a constant, isn't it? So I can pull that out. So what's my integrand? 2 pi a or 2a pi? I don't know. And then what's my integrand?
1 or just dt?
Yeah, just 1 for the integrand. So yeah, you do just write dt, right? And so when I integrate that, when I integrate 1 with respect to t, I get t, I plug in the upper limit. That's the only thing that's not going to zero out. I get 2 pi a times a over 2, which is pi a squared. That's it. It would be in square units if you had units. Now, the interesting thing is, remember this was this curve, when you rotate it, becomes part of a sphere. Does anybody remember the surface area of a sphere?
It's 4/3 pi r cubed, right?
No, that's volume. That's volume. It doesn't come up as much, but it's 4 pi a squared for the volume of a, or not the volume, but the surface area of a sphere. And the interesting thing is, oh, okay, so when you just go up to 1/2 the height here of A, which would be the radius of the sphere, you get 1/4 the surface area when you do that rotation. Because the full surface area of the full sphere would be 4 pi a squared.